Okay, we have here an examples of the excitation of metal cations. They are used in making fireworks. And the classic colors are shown here. We get this orangish color from calcium glowing, this purplish blue color from potassium. The lovely green flame is copper. The reddish flame comes from strontium, and the sodium flame comes from, or makes a lovely yellow flame. So in our unknown, we're going to do a brief flash to see if we can see evidence, and we're going to be looking for evidence of either calcium, potassium, sodium. Barium does a bright, ghostly yellow-green color, and I do not have a barium flame here. Okay. We are now going to demonstrate the known flames of our four cations that have a flame: potassium, barium, calcium, and sodium, and we're going to do it in that order. So first, to show you the flame of potassium, we're going to take our wire loop, gently touch it to the liquid, and then we're going to hold in the flame. And you see that bluish purple glow there for a second? That is the classic potassium flame glow. And we're going to demonstrate it one more time, this time through the lens, and it kind of gives a reddish glow through the lens. You see it glowing through the lens? Mm-hmm. Okay. All right, I now need to quickly clean the loop. I'm going to use concentrated nitric acid and pure water so we can perform our next test. So our second test is to show you the flame. Whoops, the potassium's still there. Let's get rid of it. All right. We want to show you the barium flame. Okay. Barium flame has a distinctive yellowish green color. So without the lens, you see that bright yellowish green kind of popping. They call it a greenish color. To me, it looks yellowish green, and it's basically gone. Through the lens, it kind of gives a ghosty look. So through the lens, you see the flames. They're kind of a brightish yellow color, or a whitish. Okay, time to clean again. We just lost a piece of barium. Stop. Okay. Do this one more time. All right, we want to be comfortable with what the flame looks like when it's glowing the brightest, and this kind of is a residual sodium flame. Calcium flame is one of the most difficult ones to see compared to sodium because they're both orangish colored. This one is just a red or orange, and it's gone. Let's try it one more time. I'm going to be bluntly honest. There it is, that reddish orange glow that we had for a second. And now we're back to a yellow-orange glow that is not calcium. So if you watch the demo of the rainbow fire, look at the calcium glow there, you get the lovely orange color. Okay, now for sodium. Sodium is so pervasive that usually once I test it, its flame never goes away, so we always save sodium for last. It is also why this lens is used, because it blocks the sodium flame from being seen. Okay, we're just going to gently touch the liquid. Okay, watch carefully. See how intense and yellow and bright that is? If you have sodium, your intensity better be that bright. It's an incredibly bright yellow flame. And keep filming. Look through the filter and the flame should disappear. Does it disappear?
No, it doesn't.
Doesn't disappear? Then we got somebody else glowing in there. Yeah, it disappears. I don't see it. Do you see it through the camera?
It did it first.
Yeah, see, the flame basically disappears. There's something residue in there, but orange flame, no flame.
Okay.
Okay, everybody see how that works? Okay.
Are we done?
We are done.
Hello, Chem 122 lab students. This is Professor Garner here. I'm the lab coordinator for the Chem 122 labs. and I'm going to be giving you a pre-lab lecture on experiment 23, your first qualitative analysis. We're going to be studying group 4, but let's talk a little bit about the purpose of these labs. So about 20 years ago, this is the way all of the Gen Chem 2 labs were taught entirely, was all semester long you did qualitative analysis. And so what it is it's a wet chemistry technique to take advantage of chemical equilibrium and wet chemistry techniques to precipitate out certain ions in solution and confirm that those ions are in solution. This has been largely replaced by instrumental analysis and modern chemistry. And so we're going to do just 2 of these qualitative analysis labs just to give you a taste for other techniques you can use if your instrument breaks down. So the objectives for today are to become familiar with qualitative analysis for the analysis of what we're going to call group 4 cations, right? So of the qualitative analysis scheme shown in the beginning of lab 23, we're going to be doing this week the group 4 cations, which is down in the lower right, and then next week we'll be doing the group 3 cations, which is on the lower left side. So we're going to be analyzing the group 4 unknowns. Let's take a look at how we're going to do that. So the best way to understand qualitative analysis is to look at the flow chart that we use in the separation of these ions, and that gives you a better view of what you're doing. It's kind of like a bird's eye view, right? So you want to kind of get a bigger idea, a bigger picture of what the heck we're doing, right? So there's some terminology associated with it. So we're going to be using the term residue, which stands for the precipitate, to label various precipitates along the way. And so the precipitates are going to be all on the left side of this separation scheme. We're also going to be using some of the solutions, and the solutions or supernatants are going to be labeled as S on the reaction scheme, and so they'll be on the right side of the separation scheme. Normally when we get to a branching area where we separate a precipitate from a solution, we use a centrifuge, and then the partner decants the solution, and one partner goes off and works on that to do confirming what ions could be present in that solution, and the other continues working on with the precipitate coming out of the centrifuge machine. Because our group 4 cations can contain ammonium ions, and some of the solutions we're going to be adding throughout the separation are going to contain ammonium ions, we need to first test for the ammonium ion before we do any adding of other solutions to the sample. So the way to perform this test is to take advantage of the fact that if we make the solution basic by adding some 8-molar sodium hydroxide, that we can give off ammonia gas. And ammonia gas has a very unique smell to it that would be easy to identify. Of course, through remote learning, we're not going to be able to do that, right? So what we're going to do is the secondary test, which is if we make a piece of litmus paper wet with water and then have it above the solution, and we get it to evolve the ammonia gas, the ammonia will react with the water to produce some ammonium hydroxide. If red litmus is exposed to hydroxide ions, it turns blue, right? So that's going to be our confirm whether or not we have ammonia in our unknown sample. So we're going to be having a mixture of unknowns. It can contain some or all of the ions, right? So we have to figure out which ones are present. So you're going to have to watch the lab demonstration video and confirm whether ammonium ion is present.
Which is to a test for ammonium. We have to test for ammonium right up front because ammonium only really has one test, and it's the smell test or the red litmus paper test. So we're going to add 5 drops of the unknown. We're going to put it on the bottom of this test tube. And we're going to compare it side by side with 5 drops of the ammonium standard. So we can have a side-by-side comparison. And again, it's important that you do not touch the top of your test tube. Okay. Now I'm going to pre-prepare the litmus paper. You need a pink litmus paper. You need it moist with a little bit of pure water. And then we're going to add 5 drops of the sodium hydroxide into the mixture. If there's ammonium ions present, they should turn into a gas similar to what we would smell, and then float up to the top of this pink paper. And you can see it turned blue just from me touching it, so that doesn't count. It has to turn blue in the circle. Likewise, we're going to do the same with the known. We're going to moisten it. Add 5 drops of the ammonia down into our known mixture. And then we're going to let, this is twice now, where it sticks to my skin more than that. So we're going to let it zoom in, and I'm going to try to tip these over without dropping them, and we're going to watch what happens to the pink litmus paper as it sits above the vapors of the ammonia. Now, if all goes well, the ammonia vapors, the smell, will reach the water, turn into ammonium hydroxide, and the litmus paper will turn a bluish color. And I don't know if you can see that.
On the left one.
This one is the unknown. We'll zoom in, but you can already see that that circle's turning bluish. So, and this is the known, and it's beginning to turn blue inside of the circle there as well. Let's move this out of the way so we have a nice white background. Okay.
In procedure 2, we're going to be precipitating out any possible calcium and barium ions, right? So the first thing we're going to do is go ahead and do a flame test. And so Professor Hammond's going to show you how to perform some of these flame tests. You end up having to use a wire loop and make sure that your wire loop is really clean, because residues on it can give us false positives, right? So what we're going to be doing is testing for various colors to see if there are any obvious indications of some of the ions that in the entire flow chart. You can see that some of them will give off green flames or orange flames or lavender flame when viewed through a piece of blue filtering glass. The way we're going to be precipitating out, though, is we're going to be making the solution alkaline and then adding some carbonate in the form of ammonium carbonate, right? And so the procedure says that we're trying to see if we have any barium or calcium. And once we get that precipitate, then we're going to have to go on to procedure 3.
We are now going to precipitate out, or attempt to precipitate out, the magnesium and calcium ions if they exist or are unknown. The first thing is to take 6 drops of your unknown, place it in a small test tube. Okay. Save that in the unknown. And now we are going to add 6 drops of cold water. We're just going to use ultra pure water. I'm going to try to do this carefully drop-wise, and that was close. No, that was, there we go, about 6 drops. The water is really not going to make that much of a difference. Okay. We are now, the important part, we're going to create a buffer with ammonium chloride. It's a lovely buffering agent. And we're going to start with 4 drops of ammonium chloride. 1, 2, 3, 4. Okay. And then we're going to make it alkaline by using concentrated ammonia, also written as 15 molar ammonia, or ammonium hydroxide. It usually only takes 1 or 2 drops. It is now quite alkaline. And then we're going to start precipitating. So we've created a buffer solution. that in an ideal situation won't touch the magnesium. And so only calcium and barium should precipitate. And we're supposed to add enough drops of this until it stops precipitating, which is kind of a trick. So as you saw, we made a precipitate. I'm going to hold it up against something dark. There we go. You see it made a precipitate. I'm going to let it settle for a moment, and then I'm going to try the other drop. And that was just 2 drops of carbonate. We had another drop. Did it go darker white? Not sure. So add 1 more drop just to be sure. Okay, that looks like it stayed about the same whiteness for me. So now that we've added enough carbonate, we're going to set it into our hot water bath, which we preheated to just below boiling for 1 minute. So we now have to fast forward 1 minute in time. But while we're doing that, we're going to start preparing a second test tube. Now we're going to centrifuge, and the secret to centrifuging is balance. You want 2 test tubes of equal volumes when you place in the centrifuge, and so this is going to be our balancing test tube. And we'll hold them up and compare them after our minute is up. We still have 30 seconds. And we'll then move to the centrifuge over here. Okay, so it's been a minute now, and it gives us a chance for our carbonates to precipitate. And our next job is to separate the precipitate from the liquids. And again, what I have to do is make the 2 heights of the liquid the same. So I can't see when I'm looking when it's sideways, so I'm going to gently add water until the 2 look the same height. That's good. A little too much, we'll add a little water this side, doesn't hurt. Okay, fairly close. So we made the 2 levels approximately the same. We now need to put it into the centrifuge, and we turn the centrifuge on, and you're supposed to close the door. And you'll listen. This one's out of balance. The centrifuge will gain speed and gain speed. And now that it's at high speed, you want to centrifuge it for 30 to 60 seconds. Okay, and we're going to call that good. Okay, and if you look carefully, our precipitate is on the bottom, and above it is called the supernatant. The supernatant should contain, well, obviously it contains ammonium ions now because we've added ammonium, but if there's any sodium, potassium, and hopefully the magnesium, if it's there, is in the supernatant. The precipitate here on the bottom should contain our calcium and or barium. Okay, and so the job is to separate. We are going to decant very carefully the supernatant into a second test tube and save that decantant for a later part of the experiment. Okay. So we're going to save that and put it aside. And remember, this is what they call supernatant 1, and this is residual number 1 according to the procedures number 2. So we are now ready to begin procedure number 3.
In procedure 3, we're going to be separating and testing for barium ions. So this is a very detailed test where we have to take the precipitate from R2 and dissolve it in some 2 molar HCl. Then we have to make it just alkaline again by adding some ammonium hydroxide. So we're really kind of doing things in test tubes drop-wise. If you add 2 drops here, then you have to add 2 drops there to go back the other direction if you're changing the whether it's acidic or basic. And then finally we're adding some drops of weak acid, some acetic acid, and drops of water, and then adding in some chromate, some potassium chromate. If we get this yellow precipitate, that confirms that barium is present. To further confirm whether or not barium is present, we're going to need to wash that precipitate and then perform a flame test. If we get a green flame, then we also have a secondary confirm that barium was present in the unknown.
We are now have our solid, and we're going to test for barium right now, but the first thing we have to do is dissolve it completely with hydrochloric acid, and the trick here is to use the minimum drops possible. Normally it takes 1, 2, or 3, so there's 1 drop, didn't work. 2 drops. How much unknown did I put in here? 3 drops. Actually depends how much carbonate. Whoops, 4 drops. And you see the solid went basically almost completely clear. We're going to add 1 more drop and that should finish it. Unless we're getting a side reaction I don't know of. And add 1 more. Problem is every drop of acid means more drops. Oh, completely clear. Yeah, exactly, completely clear. We are ready to proceed. So if you've added just enough acid, now we're going to make it basic by adding some dilute ammonium hydroxide, some 5 molar, and on average this only takes 2 drops. Again, as long as you didn't go overboard on the acid, and our concentrations are good. Alright. At this stage, you're supposed to test for basicity with red litmus paper. So we're going to do a quick test to make sure it actually is basic. And we're going to do it with this dropper. Without getting a drop, we're just going to touch it. And you see how the litmus paper turned a lovely shade of blue. So we are basic. We did it with 3 drops. Probably should have tested at 2, but it'll still work. Okay, we're going to then add some acetate. And what we're doing is we're making an ammonium acetate buffer. It says to add 1 drop of the 5 molar acetic acid. So we added a drop. And then we're going to add 4 drops of water. 1, 2, 3. 1 more drop just to be sure. Okay. And lastly, if there's barium, when we start adding the potassium chromate, the clear solution should start turning cloudy. If there's no cloudiness, it means no barium. If there is cloudiness, we should have barium. And what do we see? Well, since I see cloudiness, I need to continue. And we're going to continue by trying to make it until the yellowish solid is complete. I've done 2 drops, 3 drops, maybe 1 more drop should do it. Yep, that looks like it stayed about the same. The liquid just became more yellow. Okay, so we will suspect that we now have some barium in there. We're going to do a confirmation test, and to do that we're going to have to centrifuge and redissolve. So where's my centrifuging balancing tube? Oh, they look pretty close. Again, we need about 30 seconds at high speed. Okay, so when we centrifuge, we have the clear yellow liquid on top, and we have our precipitate on the bottom. The clear yellow liquid may contain calcium, so we're going to decant that and save the liquid for a calcium test. And that's supernatant number 2, so we'll put that one over there. Then the procedure says to wash the barium. The best way to wash the barium is actually to add some water and recentrifuge. Rinse it, add water, recentrifuge. So where's my balancing tube? We want to do a slightly better job balancing. So let's centrifuge again. Oh, and I forgot another trick. Shake it, then centrifuge. Continuing, we have now centrifuged after we did a water wash, and that's to try to remove as much of the chromium excess liquid as possible. And this liquid does not need to be saved for anything, so I'm going to discard it into my waste beaker. We now have a basically clean precipitate that we suspect is barium chromate. So we're going to confirm that test right now. Let's get the waste beaker out of the way by dissolving this and doing a flame test. So I've washed the barium chromate with the water. Hopefully that removed any calcium. And we are now going to transfer the yellow chromate precipitate to a white barium precipitate. So you add the hydrochloric acid and it should basically dissolve it, at least in part, and you'll see the solution's turning orange, the solid's starting to dissolve. Okay, and we get a lovely orange color as the chromate is shifting to a dichromate ion. Okay, it looks like it's shifted. Now we need to add this sulfuric acid, and what'll happen is it'll go white cloudy again, and that's because the solubility of barium sulfate is a lot stronger than barium chromate. Okay, let's see if we can now centrifuge. Centrifuging tube. Okay, we're now going to centrifuge this one, and the idea being we are going to completely remove the chromate. So if we do enough watches and centrifuging. Should do for round 1, and I'm going to show you a bullseye view, but you'll see the precipitate is much wider than it was before, and the supernatant is basically orange. We're going to discard the supernatant again, and by the way, this chromium liquid must be put into hazardous waste. Okay, now we're going to do one more wash just to remove any last traces of yellow that we can from the possible barium precipitate. So this time it says centrifuge and wash 3 times with water. Washing 3 times with water literally means washing and centrifuging 3 times. And we'll see if we can remove all the yellow liquid from the chromium. Okay, again, the yellow color is fading, which is a good sign. Our precipitate's still nice and white. Discard all of that. Let's do it one more time. Ooh, see how near colorless that liquid is? We could go to the next stage, but the procedure says one more washing, so we will do one more washing just to make sure. Okay, for the last time, I would say our supernatant is completely colorless. We have our white solid on the bottom. We have now washed the precipitate and removed the chromium. Okay, so it is time for concentrated hydrochloric acid. Usually you do this in your under the hood because this gives off vapors. I'm going to hold my breath. And hopefully what we're going to do is we're going to add 1 to 3 drops so that this solid just barely dissolves, and we'll have a nice concentration to go test for a flame test for the barium ion. And so we will pause as soon as I dissolve this. Well, I'm going to say this, but there should be enough of this dissolved to be able to do a flame test with what's ever in here. Now we're going to try either flame confirmation test, a barium. We have this mixture and we put it in there. We're looking for a yellow greenish glow that's not orange, and look carefully. Do we see a yellowish green glow?
I think we got it.
Okay.
Procedure 4 is going to be taking the supernatant and testing to see if there is any calcium ions in the unknown solution. So the first thing we're going to do with that solution is make it alkaline with 15 molar ammonium hydroxide. The solution color is going to change from an orangey color to a more yellow color when it's basic. And then we add 5 drops of this ammonium oxalate. Oxalate ions should precipitate as a white precipitate as calcium oxalate, and that will prove the presence of the calcium ion. Again, we're going to need to confirm that we indeed did get the calcium ion by performing another flame test, and so we're going to have to wash the precipitate and then put it in the flame to see if we have a orangey red flame, which would prove the presence of calcium ion. Moving right along, we get to finally the other branch of the flow chart separation scheme. So we're going to be testing for magnesium ions and also splitting off some of the supernatant and being able to test for sodium and potassium ions with other flame tests. But this procedure 5 is mainly to test for the magnesium ion. So there's a series of steps that we have to do to make sure that we remove any possible ions that we didn't already precipitate out. Like, so we're going to add in some more oxalate ion and see if we get any calcium oxalate, and we're also going to see if we get any barium sulfate precipitating out. Once we get that all cleaned up and we get that supernatant ready to test, we're going to add some ammonium hydroxide and some sodium hydrogen phosphate, warm it, and see if we get a white precipitate that would be magnesium ammonium phosphate. That tells us that we have the possible presence of magnesium ion, but it doesn't confirm it. So what we end up having to do then is dissolve that precipitate in HCl, add some magnesium reagent, which is paranitrobenzene resorcinol, and add 8 molar sodium hydroxide. If we get this blue lake, which is what we describe it as, this flocculent blue precipitate, then we have proved the presence of the magnesium ion.
We now have the supernatant that we collected from the barium step. It has some of the chromate color in it. We're going to try to see if we can show evidence of calcium. To do that, we're going to make it slightly basic. So we're adding couple drops of ammonia, and the color gets brighter yellow, and that tells us that we're definitely in a basic form. So we know it's basic. And now to try to precipitate out the calcium, we're going to use this oxalate. Just a word of warning, oxalate will also precipitate both magnesium and barium as well. So hopefully we did a good job separating our unknown earlier, and we're looking for any precipitate to see if it's there. And we added 2 drops. I do see any cloudiness. Remember, a negative is a result as possible. I'm going to try one more drop, but this exceeds what we're supposed to add. And I do not see any precipitate, so I'm concluding we are done with that part of the experiment. Let's pause now. That was procedure 4. We're now going to move on to procedure 5, with the liquid from the very beginning supernatant. That was this liquid right here. This liquid has a possibility of potassium, sodium, and magnesium ions. Of the three, it's impossible, well, two of them, potassium and sodium, is impossible to precipitate, so we'll have to separate those out later via evaporation and try a flame test. What we will try to go for now is to see if there's any magnesium in here. And again, if there's no precipitate, there's no magnesium. Okay, so we have it. We're going to add 2 drops of ammonium sulfate first. And then we're going to add some ammonium and boil. Now, the purpose is the sulfate and the oxalate will precipitate if we accidentally left any barium or calcium in here. So there's my sulfate. That looks good. No solid. Where's my oxalate? And we're going to now add some oxalate and look for solid. And it looks pretty good. Is there any haziness? What do we say? When in doubt, centrifuge. And I have a tiny bit. Precipitate, we don't want that. We want the supernatant. So we're going to transfer all of our supernatant unknown into this test tube, and then we can move on with the magnesium test. Okay, so we have verified that we removed both the calcium and the barium. Now for the magnesium test. What we're going to do is we take the decantant, and it says to divide it into 2 equal portions. One is to go do the magnesium and potassium test, and that we're going to need a small evaporating dish. So let's stop rolling for a second, and we're going to do both at the same time. Okay. Again, we have the supernatant that we have removed calcium and barium from. It has a possibility of magnesium, sodium, and potassium left. And the first step is to divide it approximately in half. And, whoops, I took it all. Okay, and put half of it into an evaporating dish, which we are going to do. So I just put a little drop here, and we're going to set the evaporating dish on this boiling water bath, and that'll help the water evaporate better. Once that's condensed down, we'll try a flame test to check for sodium and potassium. With what's left here, we're going to do the magnesium possible test, and so that is first done by adding a drop of the 5 molar ammonium hydroxide. That's going to make it slightly basic. Okay, we added the drop, and then we're going to add 4 drops of the sodium biphosphate. The idea being is, will it precipitate? Because phosphates precipitate with both magnesium, calcium, and barium. And this one's questionable. Says mix and warm gently for 1 minute. Oh, actually it's starting to precipitate. So this is suspicious. Having a cloudiness means there's a high possibility of having magnesium in there. We're going to proceed as if there is magnesium in there. And to do that, we're going to do the magnesium lake experiment. Okay, so definitely cloudy. Hopefully it's magnesium. And so what we are to do now is centrifuge and decant. Actually, I'm going to let this finish precipitating. I'm going to borrow my hot water bath for a moment from my evaporating dish. Just balancing that carefully. Let it heat up completely. Alright, that's enough heating time for my opinion. All right, definitely have cloudiness. Let's go for centrifuging. All right, we definitely have a precipitate. We're going to decant off the liquid. We need to save only the solid. And we're going to do one water wash, and I'm going to borrow my hot water bath this time because I put pure water in here. All right, decant the liquid. And now we're going to test for magnesium with what's left here. We are going to first dissolve this by adding 2 drops or 3 drops of the 2 molar hydrochloric acid. 1 drop, it completely dissolved. We don't have to add any more. That's good to know. Now we're going to add some magnesium reagent, which is the para-nitrobenzene resorcinol, and this will bond to magnesium and make a lovely blue color if it's there, and precipitate under basic conditions. Okay, so under acidic conditions it should have a reddish or orangish color, and one of the things we're going to add is the sodium hydroxide. That's 8 molar, and what that will do is it'll both change the color and reprecipitate any magnesium phosphate that's there. So you basically just have to wait till the color is finished changing to a purplish blue color. Okay. This is why it looks suspicious. You can see it on the bottom. Okay, we're going to hold the white paper, but you see this bluish colored precipitate that's stuck on the bottom of our test tube? That is a positive result for magnesium. So I'm going to centrifuge it one time, and when I pull it out, I'll try not to shake it as much because I kind of mixed it up. It tends to all clump together. Can we see that blue little grouping right there?
Yeah.
Everybody see that? That looks like what we were supposed to see. Okay, so that's our magnesium test. We have one test left, and that is a flame test. This is the final flame test of the experiment. We either have sodium, potassium, we have to make a decision. We've already added the hydrochloric acid to redissolve whatever these salt crystals are. And we're going to do a quick flame without the lens to look for thing, and then, hang on, we'll rinse off the lens. Rinse off the wire, flame it one more time to clean it. And then we're going to do a flame. We're going to look at the flame through the lens. And what we're looking for is for a bright, intense flash through the lens. That will be evidence of potassium.
Oh, I see.
You see it? Okay. And that concludes this part of the experiment.